Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're continuing to look at loci and complex numbers. Now, we're just focusing on one particular locus in this question, and that's a locus that has the form the modulus of z minus some fixed point, a plus bi, a and b are fixed constants, is equal to the modulus of z minus another fixed point, c plus di. We'll go straight into an example. So let's say that the modulus of z minus 4 was equal to the modulus of z plus 2i. And we had to sketch the locus of z. We've got to find the Cartesian equation of the locus of z. And we have to find the least possible value of the modulus of z. Now, it's tricky to do this if you've never seen a question like this before. But if you're wanting a go, then pause the video, have a go by yourself, and then come back to me again when you're ready. Okay, let's look at this together. So we're asked to sketch the locus of z, where the modulus of z minus 4 is equal to the modulus of z plus 2i. Now, immediately there's an issue, because these two moduluses, they're not written in the standard form. We should have the modulus of z minus a complex number is equal to the modulus of z minus another complex number. Now, 4 is a real number. To write it as a complex number, then it would be 4 plus 0i. And more importantly, in this second modulus, the plus does have to be changed to a minus. So we get the modulus of z minus, and 0 will be the real part of that complex number, and then minus 2i. Then it's written in the standard form. Now, to move forwards, there are two different methods, and they do feel very different from each other. You can consider what's going on geometrically and work out everything from there. Or you can work out what's going on algebraically without ever really worrying about what is happening geometrically. We'll do both, but we'll do the geometrical solution first of all. Now, to solve the question geometrically, you do have to be able to look at these statements and imagine exactly what they're saying, what they mean spatially. Now, what are these statements saying? What they're saying is that the complex number z, it's got to be the same distance from two fixed points. So it's got to be the same distance from 4 plus 0i as it is from 0 minus 2i. That's what the question is saying. Now, if z has to work under that restriction, the question is, well, where can z be if it's got to be exactly the same distance from those two fixed points? Well, where it has to be is on the perpendicular bisector of the line that joins 4 plus 0i and 0 minus 2i. So we'll sketch that. First of all, we'll draw the 2 points. So 4 plus 0i, it's just a real number. So it'll be 4 on the real axis. And 0 minus 2i doesn't have a real part. It's just got an imaginary part. So minus 2i will be minus 2 on the imaginary axis. Then we join those lines together, or points together. And then we have to draw the perpendicular bisector of that line. And that'll be the locus. So the perpendicular bisector of that line will look something like that. Now, I'm also going to find the coordinates of this point where the two lines cross each other, because that's going to be useful later on. Now, it's the midpoint of this line. But that means it's halfway from 0 to 4, and it's halfway from 0 to minus 2. So the coordinates of that crossing point, the intersection point, will be 2, minus 1. Anyway, that's part 1 completed. The green line, that is the locus, and we have done a sketch of it. Part 2 asks us to find the Cartesian equation of the locus. Well, that means how do we find the equation of this green line? The easiest way to do it is to find the equation of the red line from minus 2 on the imaginary axis to 4 on the real axis first. And then just using standard Cartesian geometrical methods, we'll then find the equation of the perpendicular to that goes through the point 2, minus 1. So first of all, the gradient of the line that joins minus 2 here on the imaginary axis to 4 here on the real axis will be 4 divided by 2, 2 divided by 4 rather, which simplifies to to a half. So the gradient of the red line is a half. That means the gradient of the perpendicular bisector will be -1 divided by that. And -1 divided by a half is -2. So that's the gradient of the green line. Now we know a point on the green line. We know that the point 2 minus 1 is on it because we found that just now. So if we substitute that into y equals mx plus c, and we substitute the gradient -2 in for m, then we get -1 is equal to -2 times 2 plus c. Then we can find c. So solving that gives us c equals 3. So we know that c equals 3. We'll put in 3 there on the sketch. And we know that m equals -2. So if c equals 3 and m equals -2, we can now write down the Cartesian equation of the locus of z. And the Cartesian equation of the locus of z will be y equals -2x plus 3. Now that's the geometric method. A lot of people find the algebraic method more straightforward because you're just able to follow a method without worrying too much about what's really going on. Now, the algebraic method just involves us writing down z in the form x plus iy, which is what z is. Z is just a general complex number, which is x plus iy. So we substitute that in for z into both sides, and that gives us the modulus of x plus iy minus the 4 plus 0i is equal to this here on the right-hand side. Then what we do is collect together the real parts and the imaginary parts in each modulus. So we get the modulus of x minus 4 plus iy is equal to the modulus of x minus y minus 2 into I on the right-hand side. Then we just use the definition of modulus, and that gives us the square root of x minus 4 squared plus y squared on the left-hand side is equal to the square root of x squared plus minus y minus 2 squared on the right-hand side. That's just using the definition of what the modulus means. The easiest thing to do now is just square both sides, and that gets rid of the square root. Then we need to multiply out the brackets, which will give us that. None of this looks very promising, but many things cancel. The x squareds cancel with each other, the y squareds cancel with each other. That leaves us with minus 8x plus 16 equals 4y plus 4. We can divide everything by 4 and tidy things up, and we get y equals minus 2x plus 3. And that is what we got before. So the Cartesian equation of the locus is y equals minus 2x plus 3. And that's how you'd find it algebraically. Okay, part 3 asks us to find the least possible value of the modulus of z. Now, what is that actually asking us to find? The modulus of z is the distance from z to the origin. So if we've got to find the least possible value of the modulus of z, what we're looking for is the least possible distance from the origin to the locus, which is to this green line. So the smallest possible distance from the origin to the line. That least possible distance is the perpendicular distance from the origin to the locus. So it would be the length of that purple line there, which goes from the origin to the locus and meets it at 90 degrees. And then the question becomes, how do we find the length of that line? Well, the first thing that we do is find the equation of that line. And the gradient of this purple line is exactly the same as the gradient of the original line, the red line here, because both of them are perpendiculars to the locus, to the green line. Now the gradient of this red line was a half, so the gradient of this shortest distance line here must also be a half, which is what we're saying there. The equation of the purple line must therefore be y equals a half x, using y equals mx plus c, but c is 0 because the line goes through the origin. So the equation of this minimum distance line is just y equals a half x. Now we need to find the intersection point of this line, the purple line, and the bisector, the locus, the green line. So we need to find the coordinates of that point there, where those two meet. Once we've done that, we'll be able to find out how long that line is, which is what we really want to know. Now to find that, we need to solve them simultaneously. So we need to solve y equals a half x and y equals minus 2x plus 3 simultaneously. Y equals a half x is the equation of the purple line, and y equals minus 2x plus 3 we found a little while ago. That's the equation of the locus, the green line. Solving those simultaneously gives us a half x equals minus 2x plus 3. That gives us 5 over 2x equals 3, which gives us x equals 6/5, 6 divided by 5. So that's the x coordinate at that intersection point there. And the y coordinate will be a half of that, because we know that one of the lines is y equals a half of x, and a half of that will be 3/5. So that gives us the coordinates of this intersection point here. Now that we know that, we can find what we've been asked to find, which is the minimum distance from the origin to the locus, to the green line. And that will equal the square root of 6/5 squared plus 3/5 squared, just using the standard method for finding the length of a line segment. And in this case, one of the points is 0, so it makes it a lot easier. That simplifies to the square root of 45 over 25, which simplifies to 3 root 5 over 5. So that is what we've been asked to find, the minimum possible value of the modulus of z, which is this distance here, from the origin to the locus, along the perpendicular to that line. Okay, that gets us to the end of this lesson. If you have the textbook, then turn to page 52. And in exercise 4a, questions 6 to 8, all this type of question. Thank you very much for listening, and cheerio.